Hello, statistical scholars, and welcome to another episode of Fun Times and Statistics. Today I'm going to be going through the Chapter 5 probability worksheet, which you can find in our class for our weekly folder this week. So let's get into it. A study of 1,000 randomly selected flights of a major airline shows that 769 of the flights arrive on time. What is the probability of a flight not arriving on time? So this is looking at the complement of an event. So if you want, you could calculate the probability that they are on time first, which would be 769 out of 1,000. And then to do the complement of that, we would actually do the probability of them being not on time, which would be 1 minus the probability of being on time, or 1 minus 769 out of 1,000, which in order to make your fractions like, they need to have the same denominator, so that'd be 1,000 out of 1,000 to make a 1, minus 769 out of 1,000, which is the same as the fraction 1,000 minus 769 out of 1,000. Which would be 231 out of 1,000, which is 0.231. And I know half of you are now thinking, oh, do I have to show that much work? Well, if you want to get it right, you could just write the end and hope all of your calculations were correct, but you should show some work, and then, maybe you'll get some points. Fun times. There are lots of ways to do this. That's one of the beautiful parts about math, is the freedom in which we can calculate in many, many ways. I am hoping that, you have your own way, and as long as your answer matches mine, then you are correct. All right, let's get into the blood type problem, or the why you should be afraid that people are going to kill you and steal your organs problem. So, the distribution of blood types for 100 Americans is listed in the table below. If one donor is selected at random, find the following. The probability of selecting a person with type O blood. So there are two type O's in here. There's the type O positive and the type O negative. So I'm going to add those two together to make my numerator. 37 plus, not minus, plus 6 out of the 100 people. So again, event out of total, which would be 43 out of 100, or 0.43. Alrighty. We're going to find the probability of getting somebody who has B positive, because it's important that you be positive. Ooh, lame math joke of the day. Check. All right. So B positive, that's 10 out of the 100 people. Or if you like, 0.1. Or 10%. Notice I don't write these are equal because 10 isn't equal to 0.1. 10% and 1% are absolutely not the same, and 0.1% is not the same as 10%, in case you didn't know. So we wouldn't really write that these are equal to each other. They are the same representation of a number, just written slightly differently. Fun facts about things that you don't care about, because half the students I see will write these are equal to each other. Oh, only I care. Okay, how about some A plusin'? So there's only 34 people who have A positive blood. Fun times. If you're looking for yourself on here, notice there are some very rare events like B negative and AB negative. Good times. Anyway, so, as I said before, I'm finding the probability of A plus that I can find, or A positive, sorry, so that I can find, I keep calling this A plus, so I can find the probability of not getting A positive, which is what we're actually interested in. So if you're looking at this and thinking, oh, well, couldn't I just, add up all the other ones and then do that? You know, like add everybody except for A. Yeah, you could do that. You could add all these together and add all of these together and then do them over 100, and that would give you the same result, which is, you know, 66.66. All right. So question 3 is very theoretical. It's, hey, which of the following cannot be probability values? So I'm hoping one of the things you remember about probabilities is that for any event, even the entire sample space, your probability must be between 0 and 1. So as you look at this, you know, you think about it in terms of fractions. Oh, that's between 0 and 1. That's between 0 and 1. That's a percentage. I'll come back to that. Oh, that's between 0 and 1 because it's exactly 0. We're including 0 as a possibility. My numerator is bigger than my denominator. This is not bigger than 1. So this is definitely one that we want to disclude. I think I'm just going to highlight that. I drew pictures in your answer sheets, but that was because, you know, things. So I'm going to put it in red so I know it's bad. So if you're between 0 and 1, if you think about it in terms of percentages, then you multiply by 100, and that gives you the percent, which would be between 0 and 100%, which means you can't be 120. So all the times you watch Maury Povich and people are talking about how they're 100 and 300 and 400% sure that baby is not theirs, they don't understand probability because you can't be above 100. Oof, lame joke number 2, check. All right, let's talk about mutually exclusive events. So when events are mutually exclusive, when you consider their or, which is either one or the other, mutually exclusive means they share no outcomes in common, which means they don't overlap at all or they have no intersection. So in essence, I don't overcount anything because they have nothing in common. So I can just add them together to do the or. So when I'm doing the or for this, or the union if you like, I could just do the probability of A plus the probability of B, which would be 0.6 plus 0.05, which would give me 0.65. Woohoo. Okay, now when events are independent, that means that knowing one has no effect on the other. So when you're looking at calculating the AND version of their probability, which is also known as their intersection or their conjunction, in case you care. It's the same as doing each of the events individually and then multiplying together the result. So this is how you know when you're going to use the multiplication rule for probability. And that's only when things are independent, as in knowing events about A will not change the probability in B, and knowing things in B will not change the probability of A. So we'll just multiply them together, and we get about 18%, or 0.18. Now, we are now looking for mutually exclusivity, as in they share nothing in common, and are they disjoint or not. So, event A, rolling dice and getting an even number, rolling dice and getting a 1. Well, 1 isn't even, so these are mutually exclusive. Yes, they are. Next, we want to look at it rains in Midland on any given date, and it snows in Midland on any given date. Can it rain and snow on the same day? Yes. Can it rain and snow at the same time? What do you think sleet is? Haha! So these would appear to, I'm way too excited about this, not mutually exclusive. Alrighty. Selecting a random student and they are taking a math course. Selecting a random student, that student is taking a business major, and what courses you take are often very, very interrelated. So it is very possible that a student that is a business major hasn't met their math requirement yet and therefore is taking a math course at some point, or needs to meet their math requirement and is taking a math course at that point. So therefore, we would say that these two are not mutually exclusive. I'm just liking that I don't have sentences at this point. Okay. A person's birthday is in fall. A person's birthday is in March. What season is March in? It's not fall. Okay, so if your birthday is in the fall, then it can't be in March because that's not in fall. If your birthday is in March, then you can't be in fall because March is not in the fall. Therefore, yes, these two are mutually exclusive. Fun times in math land. Oh, I just realized that I don't think I really need Minitab for this, but it's cool. Let's finish this up. So, there are 43 students in a math class. If 5 receive a grade in A, 13 receive a B, and 18 receive a C. Sorry, 45 students in math class. What is the probability that a randomly chosen student receives an A or a B? Now, here's where you need to be careful. Normally when I do an OR, I have to be careful and watch out that I don't overcount people that fall in the first group and the second group. But you can't receive an A or a B. You know what I mean? Like, you can't receive both. You either got one or the other. So that means I can straight up add these suckers. So I would just do 13 plus 5, because that's my A's, divided by my 45 students. And if you calculate that, that's 18 divided by 45, which is 0.4. Good times in math land. That was pretty nice. Okay, what's the probability that the student did not get a C? So first I'm actually going to calculate the probability that they got a C. That was funny. Which is 18 out of 45. So then to do the complement, the probability of not C. I didn't just say not C. You know, so you do 1 minus the 18 out of 45, which I should have calculated what that is. Oh wait, that's the same as the one above it. Oh, that's lucky. 0.4. Okay, so the not one that I'm interested in, which is the actual value I want, is minus 0.4 or 0.1 because I can't seem to type the right thing today. So that's 0.6. Good times. Math times. Okay. So if C or higher is passing the class, what is the probability that the student fails the class? Oh, I regret writing this problem. Okay. So here what I want is I want to know the probability you get an A, or you got a B, or you got a C, because then if I can figure out that, I can do the complement and get the probability that they failed, as in they didn't get an A, B, or C. Okay, so luckily I have A or B above, so I can use that and then add C to it. So I can take my 18 out of 45 and then add my C, my C's, which were 18 out of 45 also. Oh, okay, yeah, because I'm just stealing it off of here, which when you add those together, you get 36 out of 45. I promise I will never do that again. I just realized how horribly annoying that's probably when you read this recording. Okay, so now on to complement land. So we're going to do not the event above. Not A, B, or C. Wow, my capitalization is working wonders today. Watching me type this is probably like super fun to, time. I don't know, whatever. 1 minus 0.8. Oh, about 20%. Actually, that's not bad for a failure rate, in case you were wondering. For a hard class, that would be, like, good. For an easy class, you'd be like, maybe your teacher got some problems. Okay. Alright, so 20% failed. Oh, sadness. Oh well. Moving on. As you should with your life. Alright, you and a friend are both enrolled in the stats course. Your professor mentions that 28% of students are certified an A every semester. Damn, I want to join that class. If the following parts assume the event you are earning an A is independent of your friend earning an A. Maybe you guys just don't study together. It could be. Alright, let's find the probability that you will earn an A. Well, if you earned an A, then, that's... I'm going to write this weird. U equals A. I think I wrote it better in the answer sheet. Oh well. That's 28%. Aww. You not A. I'm talking like a cave person. 1 minus 28%, which is 72%. Aww. It's not very, well, I mean, it's kind of low, but there's other things there, like B's. Those are good. Okay, find the probability both you and your friend will earn an A. So to find the probability U equals A and friend equals A. Oh, I love how I'm writing this. It's stupid. Okay, since you're independent, and this is an and, we know that that's going to be the same as doing the probability that U equals A times the probability that friend equals A. I almost wrote fiend. Which is going to be 0.28 times 0.28. which is 0.0784. I'm using a calculator to do that, not Minitab, in case you were wondering. And I'm also not bringing up the calculator because you guys know how to multiply. You got this far. You can do this. Okay. Find the probability that neither you nor your friend gets an A. Aww. So you, not A. And friend, not A. And again, we're going to use independence. So that's definitely you, not A, times, oop, not multiply, not subtract, friend, not A. I'm starting to get sad about this problem. You get an A, and you get an A, and you get, okay. We know what the probability is to not get an A. That's 72%. So 0.72 times 0.72, which is 0.5184. Woohoo! Again, terminates, so keep it all. At least one of you gets an A. And here's where we need to be kind of convoluted. So if you look at the options, there's really 4. You both get an A, at least one of you gets an A, and neither of you gets an A. So we've already found 2 of those events. So we can use complements to find this remaining event. Since we've already found the, hey, we both get an A, and the, hey, we both don't get an A, at least one of you gets an A is the other options. So we'll subtract in order to get this. So we're going to do the probability is at least 1. Would be the complement of no one gets an A. So 1 minus event D, which was 0.5184, bonk. It's 0.4816. And the event I was mentioning earlier was the probability at least that one of you gets an A, which would be the complement of these 2, not just this one, which is what this one is. So carefulage. There's a lot going on in this A land. So maybe let me do that one for fun. So let's say you want to find the probability that one of you gets an A. Now that would be the probability friend gets A, or friend gets A. And so that one would be the one minus that neither A both A, which is events D and C. So that one would be 1 minus 0.5184 minus, where is it? 0.0784. Which, if you calculate that, is 0.432. Okay. Notice that at least one of you gets an A is a little higher because it includes the probability that both of you get an A. One of you gets an A is lower because it's just exactly 1 and not 2. Okay. I hope you enjoyed this video. Sorry it's so long. See you in a little while.